We have 5 different teams to honor this evening with either an award of excellence or an award of merit. So I'll be able to present now the first award winner in the category of infrastructure. This award in infrastructure goes to the team of Guy Nordson and Associates and John A. Martin Associates for the Hammer Museum project at John V. Tooney Pedestrian Bridge in Los Angeles, California. Designed in collaboration with Michael Maltzin Architecture, the John V. Tooney Pedestrian Bridge spans a length of 36 feet across the open courtyard at the 2nd floor of the Hammer Museum, connecting museum galleries from east to west. Where the bridge connects with the building's pre-existing structural base, it widens to a maximum of 29 feet 6 inches and narrows to a minimum width of 10 feet at the center. The bridge is composed of a structural concrete slab on a composite metal deck spanning between architecturally exposed steel beams and a seamless 3/16-inch perforated steel guardrail. 14 circular glass lights are cut into the bridge's deck to provide light in the courtyard below. The merits of this pedestrian bridge design include its elegantly curved geometry, both in plan and in elevation, as well as the surgical intervention of the existing structure, which resulted in almost invisible connections. And coming from a guy like myself who designs connections for a living, hiding the connections is one thing, but we'll go with that. The new bridge not only fits perfectly within the shape of the existing courtyard, but also seems to be hovering between the exterior walkways. The connections were designed so as to limit the impact of the bridge addition on the existing building structure in the event of an earthquake. A combination of sliding and fixed supports enables control of the distribution of sizing forces, as well as human-induced vibrations. The stiffness of the perforated steel guardrail, which acts as a slender upturned beam, also contributes to the bridge's performance under vibrations. The bridge is an example of successful collaboration with the architect, engineer, and contractor. It was built both on budget and on schedule while causing minimum disruption in museum operation. SEAOSC recognizes Guy Nordson and Associates and John A. Martin Associates with this award of merit in the infrastructure category. Thank you. One of those representatives are here. We'd like to come up and accept an award. The next award showcases a retrofit alteration project needed for a structure to keep up with the rapidly moving pace of the entertainment industry. The Forum, a venue many of us are likely familiar with, did not want to get left behind, but instead remain a staple of what an excellent entertainment venue should be. This retrofit alteration award of excellence is presented to Severed Associates for the Forum in Inglewood, California. Sits on the cables. The inward force pull from the cables is countered by a compression ring. All the heavy lifting is done by the cables. Music acts today are bringing a heavier and heavier gear, and they want to suspend it all from the roof ceiling rather than build their own structures, and the Forum's roof cables just did not have enough reserve capacity. The enhanced capacity needed could not be obtained with conventional reinforcement design techniques. A completely out-of-the-box solution was needed. The structural engineers turned the inspiration to the giant cathedrals of ancient Europe. They are dome structures, which have a compression ring at the top in the form of an oculus and a tension ring around the perimeter to resist the dome's natural tendency to flatten out. In a dome, the forces radiates outwards. At the Forum, the roles are reversed. The compression ring is on the perimeter and the tension ring is at the center at a slightly lower elevation. This is a tension structure. The ring outside is pulled inwards rather than outwards because the sag in the cables causes the force to radiate inwards. The structural engineering logic was to now create a modern day version of a dome and marry a new compression structure to the existing tension structure. It would relieve the forces on the existing outside ring and generate the extra capacity. So the team created a new structure within the volume of the existing roof and merged it with the existing structure in the same plane. taking advantage of the subtle curve of the roof. They introduced a compression ring, like an oculus in a cathedral, except they fashioned it out of steel to bring the entire compression structure together. It then slid the new ring through a hole in the old ring and tied the new compression ring to the existing tension ring directly below it. The combined structure now does all the heavy lifting. The cables continue to support the roof as well as take up any unbalanced rigging loads. After this out-of-the-box design was complete, it successfully held the heaviest concert in the world, at least in terms of roof loading. That concert was the 2014 MTV Music Awards that went off without a hitch. SEAOSC recognizes Severin Associates with this Award of Excellence in the Retrofit Alteration category. If a representative here, please come up to receive the award. The next project is the first of our 3 awards in the new construction category. This project shows a cohesive team approach, even though there was 11 participating firms, and showing that can add significant value to a project. This award of merit goes to TMAD, Taylor, and Gaines, Sutter Health Eden Medical Center in Castro Valley, California. The project is a new state-of-the-art $230 million hospital with a vision of creating a landmark medical center to provide the best care for the community. For the first time in the U.S., an 11-party integrated project delivery team, including owner, structural engineers, design teams, and contractors, all co-signed an integrated form of agreement. Must have had all really good attorneys working for that. Yes. Requiring them to work collaboratively, fully use 3D BIM and lean practices in a shared risk-reward environment.
It's over there.
The project consists of a 7-story, 230,000 square foot hospital building, central utility plant, and several canopies. The site is a half mile from the active Hayward Fault, causing the highest seismic design requirements in California. A robust structural system combined special reinforced concrete shear walls and special concentric brace frame systems was designed. The major challenges included exterior of the building with complex interfaces of glass, precast panels, metal panels, and a signature 120-foot tall complicated spire. The project was very successful with all the owner's goals met. Project team used innovative technology to overcome challenges and complete the project on time and on budget with construction changes under 15% of the estimated for comparable projects. The project has won numerous awards and has been on the cover page of Engineering News Record in May 2009 and September 2011, and Modern Steel Construction Magazine in November 2013. SEAOSC recognizes TTG with the Award of Merit in the new construction category. If a representative please come up. Many of us were there. This project, the San Marcos High School, receives an Award of Merit in new construction and goes to John A. Martin and Associates. After completing construction in late 2013, San Marcos High School opened a new 420,000 square foot campus, more than doubling the square footage on the previous campus in January of 2014. The new facilities transformed an existing 1,800 student single-story campus into a 3,000 student state-of-the-art multi-story high school. These new facilities include a variety of special services, including college preparation, math, science, technology, performing arts, and special education programs. The new SMHS campus featured 7 new buildings, which utilized tilt-up concrete, cast-in-place concrete, and structural steel. Some of the campus highlights include a 2-story performing arts center with a 400-seat theater, a 2-story athletic center and 3-court gym, a 3-story academic building, and a 1-story academic building. The $136 million modernization utilized a phased construction schedule, allowing the school to occupy buildings as they were completed. Tilt-up construction was the preferred construction method for the majority of the campus based on 3 critical concepts: sustainability, aesthetics, and schedule. The owner and design team employed many sustainable strategies, including the use of recycled materials in concrete mix designs. In addition, many materials were locally sourced, reducing the carbon footprint for the material transportation. The team took advantage of concrete's thermal properties, which allowed interior spaces to stay cooler, significantly reducing the demands on the campus's mechanical systems. Concrete serves as both a durable and architecturally accommodating material. The tilt-up construction utilizes a smooth slab-on-ground grade casting bed. This allows for precise construction, minimizing architectural blemishes and defects from the finished surfaces. In addition, tilt-up construction allowed for an accelerated construction schedule by significantly reducing construction time compared to traditional cast-in-place concrete. By casting the wall panels on site, the contractor was able to efficiently sequence the wall panel construction. With over 300 wall panels, the time and material saved were quickly realized. SEAOSC recognizes John A. Martin Associates with the Award of Merit for New Construction category. Please come up together. To achieve the owner's desire of a campus landmark by resolving complex programming and site conditions. Lastly, what structural engineer doesn't like exposed structure? The new construction award of Excellence goes to LPA Incorporated for the California State University Northridge Student Recreation Center. The 3-story, 130,000 square foot recreation center serves as a student population of 36,000 with 6,000 average daily visits and is funded entirely by student fees. The program includes fitness areas, 3-court gym, multi-activity court, running track, climbing wall, racquetball, multi-purpose studios, administration, lockers, and aquatic center. The facility was envisioned to become the hub of student life on the primary commuter campus. Completed in January 2012, the facility construction cost is about $47 million. The major challenge on this project was to accommodate the program on a long, narrow site dictated by the campus master plan, while addressing its poor solar orientation, urban edge condition, and the 100-feet clear span of the basketball court space on the 2nd floor, as well as the primary glass wall east elevation. Located in the most seismically active region in Southern California, the building is constructed on a site adjacent to the infamous concrete parking structure that collapsed during the 1994 Northridge earthquake. The design solution engaged the transitional nature of the site by creating a fold that responds to both climate and surrounding contexts. Sun protected and accessible on the campus on the west, open, revealing, and dynamic to the surrounding community on the east. The building's lateral load resisting system consists of special concentric steel brace frames and buckling restrained brace frames. These brace frames are exposed in many locations to create openness to the facility. Round hollow structural steel sections are used extensively throughout the building. The main structural challenge is along the primary glass east facade. The steel tripod columns are designed to support gravity loads as well as lateral loads. Due to their inclined angle, the tripod columns act as braces in the seismic force resisting system. In order to protect these tripods from losing their gravity load carrying capacity during a major earthquake, seismic fuses, or BRB frames, are strategically placed on the first floor alongside the steel tripod columns. These fuses are designed to carry a majority of the seismic loads to relieve stress concentrations on the tripod columns. A nonlinear pushover analysis was performed to ensure failure occurs in the fuses prior to overstressing the inverted tripod columns. This design works seamlessly with the architectural aesthetic and openness of the human billboard. This integrated design approach and innovative structural design created an exciting and lively place to see and be seen, where students can work out, hang out, and relax. SEAOSC recognizes LPA with this Award of Excellence in the new construction category. Please come up to get your award. So that brings us to the end of the awards portion of our structural engineering excellence. But I wanted to take a time to thank all of